In today's session at Medical Sciences Made Easy, we want to discuss drug elimination. In the previous video, we have looked at drug metabolism, that is biotransformation, which we look at phase 1 and phase 2. And the major importance of biotransformation is to make the drug water soluble to enhance elimination. So, drug metabolism acts to enhance drug elimination, which is our topic today, that is excretion or elimination of the drug from the body. And as we begin, we remind you to subscribe, like the video, and share the comments so that we can continue growing. So what is drug excretion, or what we call elimination? Drug elimination, this is the process, it is a part of pharmacokinetics, or it is a part of pharmacokinetics, that is PK, which deals with removal of drug from the body. After the drug has done what it's supposed to do, we are seeing the process, how can it be removed or excreted from the body. And the major sites of drug excretion we shall be discussing. The major site is the kidney or renal. You can call it kidney or renal. This is the major site. So the major site of drug elimination is the kidney or renal. But we have other sites like hepatic, whereby this one is via bile. We have other sites like pulmonary, that is through the lungs by exhalation. Pulmonary, that is by exhalation through lungs. We have skin, through the skin, that is in form of sweat. We have through the eye, that is tears through the eye. We have also through feces, that is stool. You can see we lose some drug through that. Then another one is through breast milk. You can see also some drugs being eliminated. Another one, we can see them being eliminated via saliva. So these are different routes, but the major one being kidney as the major site of drug elimination. And after looking at the major sites of drug elimination, we want to look at what we call drug clearance. And what is drug clearance? This is calculated by getting the rate of elimination, the rate at which these drugs are eliminated. You divide by the plasma concentration. So when you get the rate of drug elimination and you divide by plasma concentration, you get what we call clearance. And this clearance we can use, you can get clearance for the renal, we can get clearance for the kidney, for the liver, clearance for the skin, and we can use it to calculate what we call total clearance, whereby total drug clearance is clearance of the renal plus clearance of the hepatic, that is liver, plus clearance of pulmonary, that is through lungs, then plus clearance of other sites. So when you sum up the clearance through all the sites, we get what we call total drug clearance. And after seeing this one, now we are going to see how are these drugs eliminated. And they are eliminated via kinetics, whereby we are going to discuss first order and zero order kinetics according to Michaelis-Menten. And under first order kinetics, we are going to see that the rate of drug elimination is constant per unit time is constant per unit time, but this drug elimination is directly proportional to concentration. That drug elimination is directly proportional to drug concentration. Meaning, the higher the concentration of the drug, the higher the rate of elimination. Much as it is constant, we're going to see that when a drug, for example, is at 100, the rate of elimination is also going to be high. So we shall see that this one will be high. Then if we take the half-life. If it goes to 50, we see it also decreases at a rate at a certain half-life, and then it becomes constant after attaining a steady state. So when we are plotting this curve, we shall find it is a linear curve. This one becomes a linear curve. This is a linear curve. And why do we say that the rate of elimination is dependent on concentration? We are seeing when the concentration is high, also the rate of elimination is high. We see when the concentration begins to decrease, also the rate or the exponential steep starts to decrease. When we reach here, we are seeing it decreasing as the concentration reduces, also the rate of elimination reduces. So the curve is exponential. At a higher concentration, it is steep. Then at a low concentration, it is slow. That is what we say, that it is dependent on drug concentration. And we normally see this under first order kinetics. Half-life is also constant. The half-life remains constant for this concentration. So this is what we can discuss under first order kinetics, whereby the rate of elimination is depending on the drug concentration, whereby we have said when the drug concentration is high, rate of elimination is high. When drug concentration is low, the rate of elimination is slow. Then, which is different from zero order kinetics, whereby here still the rate of elimination is dependent, is constant per unit time, constant per unit time. So if we draw a graph of time against the drug plasma concentration, we are going to see that the rate of elimination is not dependent. Here, the rate of elimination is not dependent, or we can say it is independent. It is independent of drug concentration. So here, under zero order, the drug has reached steady state half-life, and even though you continue increasing the dosage, or we have some drugs which portray this zero order kinetic, whereby the rate of elimination is independent. Even when it is low, the rate of elimination is the same. So here when we plot the curve, we obtain a non-linear curve. Here we obtain a non-linear curve showing that the rate of elimination is not depending on the concentration. It does not depend on the concentration. And this one is, it occurs in a few drugs that show zero order kinetics include phenytoin, which is an anticonvulsant. We see aspirin, then we see alcohol, like ethanol, and also warfarin, which is an anticoagulant, also showing zero order. So drugs which show zero order kinetics are very few, which include phenytoin, aspirin, alcohol, and warfarin. Whereas the zero order kinetics, here many drugs are eliminated by first order kinetics, which depend on the concentration. So when you increase the concentration in the first order, the rate of elimination is high. But which is different from zero order kinetics, whereby it is independent. So even when the concentration of the drug in the plasma is very high, the rate at which this drug is eliminated is independent. It remains at a constant rate. So that's why it is very dangerous for these drugs. Whenever they are given in higher concentrations, they are very toxic to the body because the rate of elimination is slow, even when the dose is very high. So that is what we can discuss: first order kinetics versus zero order kinetics. And the major thing you have to know is the examples of zero order kinetic drugs, because for the ones of first order, there are many exceptions, with the exception of these ones, which show zero order kinetics. And as we are moving on, we also need to know and understand about drug half-life, whereby drug half-life is the time taken. This is the time taken for a drug to reduce, for a drug concentration to reduce to half. That is 50% of its original value. If the drug original value is 100 milligrams, we want to see the time taken for it to reduce by half to go to 50 milligrams. That is what we are calling drug half-life. And this drug half-life is the one that enables us to understand the interval between different doses of a certain drug. Because we are going to see, if we are applying first order and zero order kinetics, we are going to see that at the first point here, which is whereby this is the first order kinetics, then this is zero order kinetics. When the drug is still increasing with concentration of this drug, we see that after a time, after like 4 half-lives, at the 4th half-life and the 5th half-life, we see it attains what we call steady state. Steady state, what does it mean? Is that as you begin to give a drug for the first time, we see it be continuing to increase. The trough continues to increase. When you give the dose for the 3rd time, it continues to increase. Then it reaches a time whereby the trough becomes constant. And when it becomes constant, from this point to this point is what we are calling steady state. Steady state concentration of the drug. And this one is attained after between 4 to 5th half-life of the drug. So this half-life is very important, that we can always know the drugs at the intervals. So we're going to see drugs with shorter half-life. They are given frequently compared to drugs with longer half-life. You'll find drugs with longer half-life are given OD, that is once a day, whereas drugs with smaller half-life are given like 3 times a day or 4 times a day. But to attain a steady state, as a student, you have to know that it is attained after 4 to 5th half-life of the drug. That's where we attain a steady state concentration in plasma. So that's why some drugs, we take them for 3 days, others we can take them for 5 days, depending on when they attain a steady state concentration, which can exert its pharmacological response. As we end with this session, we can end by looking at the factors that affect the rate of drug absorption. And among the factors is the blood flow to the kidney, as we saw that the major site is renal. So if the blood perfusion to the kidney is high, even the rate of elimination is high, because it will increase the GFR, which is the same thing with the plasma protein concentration binding. Whenever many of the drugs are bound to the proteins, little will be filtered within the glomerulus. So the higher the plasma protein binding, less of drug is excreted. Because this, when it is bound to albumin, it cannot be filtered through the glomerulus. Then solubility, this one affects tubular secretion and reabsorption, whereby drugs which are lipid soluble, they are reabsorbed into the blood circulation, so they have lipid soluble drugs have low rate of elimination compared to water soluble drugs. That's why we see biotransformation occurs to convert lipid soluble drugs to water soluble drugs to enhance their elimination. Because once they are lipid soluble, when they are in the kidney nephron, they are reabsorbed back, hence reducing the rate of excretion. Then pH also, we can talk about it, whereby pH, you're going to see that acidic drugs are best excreted in alkaline medium. So when you have acidic drugs like aspirin, to enhance its elimination, you can always do it by alkalizing urine by adding sodium bicarbonate. And when you add sodium bicarbonate, urine becomes alkaline and aspirin is easily excreted. Then drugs which are basic in nature, like amphetamine, it is easily excreted in acidic by acidifying urine by adding ammonium chloride. When we add chloride or some weak acid, we enhance elimination of basic drugs like amphetamine. So example of an acidic drug which is enhanced by alkalization of the urine is aspirin, whereas the basic drug we can give is amphetamine, which is basic and is enhanced by acidifying urine. Lastly is drug interactions like probenicid, that when you take like penicillin, when you take penicillin drugs together with the probenicid, this probenicid, it inhibits their elimination, or it prevents their elimination. So whenever you are on penicillin treatment, you have to avoid taking probenicid because it slows the secretion of penicillins and enhances this probenicid. It also, for it, enhances excretion of uric acid. Uric acid is enhanced, whereas penicillin, it is slowed down. So these are the factors: blood flow, plasma protein binding, solubility, pH, and drug interaction like probenicid. These ones, whenever you're asked in an exam, you can always remember those 4 factors that affect the rate of drug elimination. Thank you so much for being with us, for choosing at Medical Sciences Made Easy to be your learning center at the comfort of your home. May the good Lord bless you.